All right, Algebra 1, I think I called 8.1 pre-algebra. Sorry about that. We are doing more with exponents. So we have again this is 8.2, page 495. In your book, power exponent base, remember this is a power, the whole thing. The exponent is this little number, the base is this big number right here. So our key concept, write this down, quotient of powers property. Let A be a non-zero number. That means when we're dividing, we never can have a zero on the bottom. And it says, to divide powers having the same base, you subtract the exponents. So in this case, a to the m over a to the n equals a to the m minus n. All right? So in this example, this is 4 to the 7th over 4 to the 2nd. So you would just subtract them. That would be 4 to the 5th. When you're dividing, then you subtract. Remember, when we were multiplying, we added. Now we're dividing, we subtract. So let's take a look at these. And I got a couple different ways that I do these. So I want to show you where that comes from. If we write this out the long way, 8 to the 10th means 10 eighths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over 8 to the 4th, which is not that. If 4 eighths, I do not know what's going on. Okay, so now remember, you can cancel out things that are the same. So if I cancel, maybe that's what I was doing, the same number of eighths on the top and the bottom, I would have on the top 1, 2, 3, 4, 5, 6 eighths left, which would be 8 to the 6th. So look at the little property. What is 10 minus 4? 6. So that's where it comes from. So you don't have to write that out. You can just subtract. So the bases are the same, so the answer stays there, and it's going to be 9 minus 3, which is 6. So negative 3 to the 6th. Now this one, what we need to do is simplify on this top before we can subtract. The bases are the same, so you add. So it'll be 5 to the 12th over 5 to the 7th, and we can subtract them. 12 minus 7 is 5. So it will be 5 to the 5th. This one, times, this is like over 1. We can take this as fractions, so it's going to be x to the 6th on the top and x to the 4th on the bottom. You subtract x to the 2nd. So this is going to be 6 to the 6th, because 11 minus 5 is 6. This is going to be negative 4 to the 7th, because 9 minus 2 is 7. We'll simplify the top. That's going to be 9 to the 7th over 9 to the 2nd, so it's going to be 9 to the 5th. This is like that one example, put a 1, so you're going to have a y to the 8th on the top over y to the 5th. Subtract, it will be y to the 3rd. All right, so our second key concept box here, notice there's a lot of key concepts, is the power of a quotient property. To find the power of the quotient, find the power of the numerator and the power of the denominator and divide. So this is a over b all to the m. So just like we did with the other, is you're going to give each one of them the power. So it's going to be a over m and b over m. And then you divide out the answer. So 3 halves to the 7th, that's supposed to be a 7, would be 3 to the 7th over 2 to the 7th, and you divide it out. What is 3 to the 7th? You'd have to get the answers, use the numbers, and do it. So this is going to be x to the 3rd over y to the 3rd. Now we can't do anything because the bases aren't the same, so we're done. So this is going to be negative 7 to the 2nd over x to the 2nd. And they went ahead and, if you can do the 7 to the 2nd. Okay. So let's see here. This, just like we did before when we were multiplying, everything in here is going to go to the third power. Everything. This is going to go to the third power. This is to the third power. So you're going to have 4 to the third power times x to the 6th, because there's already 2 there, over 5 to the third, y to the third. So we'll do out our numbers. 4 times 4 is 16, times 4 is 64, x to the 6th. 5 times 5 is 25, times 5 is 125 over y to the third. And I don't think that those reduce. And it's just taking them step by step. There's a lot of steps, so don't try to, don't be overwhelmed when you look at all of this. Okay, I don't know what that, okay, that's a 5 right here. That is a 5. So we're going to go a to the 10th over b to the 5th. And we're just multiplying everything here. Times 1 over 2a to the 2nd. So we have a to the 10th right here over 2a to the 2nd, b to the 5th. Now look at the a's. They are like terms basically, so we can subtract those. So that will be 10 minus 2 is a to the 8th, because there's more a's on the top, 2b to the 5th. That's a little crazy. There it is. Yep, we did it. Okay, so this one's going to be a to the 2nd over b to the 2nd, and you can't go any farther. This one's going to be negative 5. We'll just leave the negative with the 5 to the 3rd over y to the 3rd. So that's going to be negative 125 over y to the 3rd. This one's going to be x squared, 4 squared, y squared. That's going to be 16. X squared over 16 y squared. Now here's where it's going to get fun. All right, so on this one we raise everything to the third power. 2 to the third, s to the third, 3 to the third, t to the third, t to the 5th over 16. So 2 to the third is 8, s to the third, t to the 5th over 16. 3 times 3 is 9, times 3 is 27. What's 27 times 16? 432 t to the third. Okay, so the t's are the same, so we can subtract those. So 3, it'll be t to the 2nd. And I look at it this way. These 3 cancel with 3 of these, leaving 2 of them. So that's 8 s to the 3rd, t to the 2nd over 432. I wonder if 432 can be divided by 854. So we can reduce 8 goes into 8 once, 8 goes into 432 54 times. So s to the 3rd, t to the 2nd over 54. Wow, that's fun right there. It's good stuff. All right, example number 4, a factorial tree. To construct what is known as a factorial tree, begin with a single segment, the trunk. Okay. That is 1 unit long. As in step 0, add 3 shorter segments that are 1/2 unit long to form the first set of branches. So we start off with a segment like this, and then we do 3 branches like this, 2, 3. Then continue adding sets of successively shorter branches so that each new set of branches is half the length of the previous ones. So then you add 1, 2, 3, 1, 2, 3, 1, 2, 3, and then shorter 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3, and so on. Okay, maybe the picture in the book is a little bit better, or maybe they'll do it here. Here, watch this one. Step, there's the half, then a little more, then more. Make the table of new branches at each step for 1 through 3. Write the number of new branches as a power of 3. Okay, so step 1, let's go back here. We added here in step 1, we added 3 branches. Okay, so that's going to be 3 to the first power because there's only 1 3. Here we added 1, 2, 3, 1, 2, 3, 1, 2, 3. So here we added 9, which is 3 to the third. 3, 6, 9, 12, 9 times 27, which is 3 to the, sorry, that's only 3 to the second. This is 3 to the third. So step 4 would be 3 to the fourth. Write the number of new branches as a power of 3. Okay, so how many times greater is the number of branches added at step 5 than the number of branches added at step 2? So step 5 would be 3 to the 5th. So 3 to the 5th and 3 to the 7th would be there 3 to the third more. Because we would subtract them, there would be 3 to the third more. So here's step 2, right here. Step 5 would be 3 to the 5th. How many more is this than that? So it would be 3 to the third more. 27 more branches. Add a column to the table for the length of new branches at each step. What is the length of the new branch added at step 9? So the length of the new branches are half of it. So it would be 1/2 to the 9th, which is 1 over 9. 2 to the 9th would be 1 over 512. That's how little it would get. The length of it would have to be 5. Whew, be little. They wanted to add that new one. All right, example 5. The luminosity in watts of a star is the total amount of energy emitted from the star per unit of time. The order of magnitude of the luminosity of the sun is 10 to the 26th watts. So that means that's what it's close. They're rounding that number for us. The star Canopus is one of the brightest stars in the sky. The order of magnitude of the luminosity of Canopus is 10 to the 30th watts. How many times more luminous is Canopus than the sun? How many times more? Well, that'd be 10 to the, well, this is 10 to the 30th and 10 to the 26th, so it's 10 to the 4th more. Seems too easy, you guys. Did I get it? Yeah. So Sirius is considered the brightest star in the sky. Sirius is less luminous than Canopus, but Sirius appears to be brighter because it's much closer to the Earth. The order of the magnitude of the luminosity of Sirius is 10 to the 28th watts. How many times more luminous is Canopus than Sirius? 10 to the 2nd. I believe 10 to the 2nd. Yeah, because it was 10 to the 30th. There we go. All right, be careful. It's easy to make mistakes on this. Just take each number individually, step by step. Again, be careful of negatives.